you're going to
Everine
get some
and Gina?
questions.
Oh, that's even better. Okay. Anyway, thank you. Thank you for this wonderful invitation. I really appreciate it. And I apologize for the lighting here. I'm not in my office, nor am I at home, because my home is being remediated from mold. And the remediation process requires that I evacuate. So I'm at some other residence, some distance from Seattle, and I have no control, easy control over the lighting. So apologies.
Well, it turns out, Jerry, none of us have control.
Yeah, we're not in full control of our
We
life.
are not in full control. But on this particular day, launching the worldwide the water community and our platform, the whole platform that is bringing us together as a community, we saw this as a perfect opportunity to get you on record, because we know so many people want to know about your work, and that you're being interviewed all the time, and you're often being interviewed about what you've done. And we relish all those interviews, and we will spread them as much as we can. But we really wanted to ask you about what you want to do. And we know you are up to some things. Everine has mentioned a couple of times that you have some books cooking inside of you, and I happen to know that one of them is quite well along the way. And we'd like to get you on record in this interview to talk about the work that you are currently doing on a book you're writing, and then the other books that are waiting in the wings. And we know you have some big ideas there, and we'd love to hear about that. So we wondered, Everine, do you have any specific questions you want to address to the book, or should we just get him to talk?
We just get him to talk.
Okay, well, thank you.
I love that.
I'm really flattered by your interest. In fact, there are 3 books in process. So let me just outline, and then I'm happy to talk about some topics within them. Perfect. And all of the books are, you might say, radical, radical in their thinking, but I prefer to think of it as a truth-seeking rather than radical. And the first one is about the role of electrical charge in nature. And of course, that doesn't involve water, as I'll talk about in some moments. The book is essentially done. I'm just waiting for my dear son, Ethan, who's the illustrator. And if those of you who may be familiar with my 4th phase book, without Ethan's wonderful artistic work, the book would not have been what some people are claiming. He's amazing, but he's busy remodeling his home, and therefore I have to wait for him.
The whole world has to wait. Can you get him to move along, please?
I'm going to send him this video, and so maybe that will prompt him. He has promised that he's going to do it, but his family is cramped into a very small space during the construction, and he's the general contractor, and it will be artistically beautiful, but there's a bit of pressure for him to get it done, and so I'm waiting. So that's book number 1. Book number 2 is also, I wouldn't say done, but it's well along, and it has to do with the structure of the atom. And I think the current structure of the atom is not correct, and I can explain why. And in the book, I'm proposing a different model, which again is not all that radical. Chemists 100 years ago proposed something similar. I think we have to revisit the structure of the atom, which is, the basis not only of water, but everything. And so that's really important. And third is on my agenda, I haven't really started it, is a book on physiology. And I think the physiology of the cell, physiology of the body, you can read thick physiology books of 1,000 pages, and they're crammed with information. And I think that information, a lot of that information is not correct. And the book will, I hope, explain why I view much of that material as incorrect and my own speculations as to what might be correct. And this is a major project that's going to take a lot of time. And probably I'm just in the process of outlining it. I haven't gotten too far, but that's number 3. So I'm prepared to talk about book 1, book 2, maybe even some of book 3.
Yeah, I'd like to move backwards because you know, we never know. I think that top of mind, the physiology in the cell, even though you haven't developed the book quite yet, we'd love to hear why you wanted to address that and what you think might be missing.
Well, yeah, why I want to address that is I would like truth to come out. You know, you read the standard physiology book, and in many cases, for me anyway, I scratch my head. A good example is how the kidney works, for example. And I remember taking a course in physiology as a graduate student. It was the same course at University of Pennsylvania that the medical students went through. This is what they learned, and it's what I learned. And I remember scratching my head, trying to understand the mechanism about the kidney. I couldn't do it, and I thought, well, I must be pretty stupid. That pervades my mind right now. But I've come to the conclusion that, you know, it may not be that the reader is so stupid as to be unable to understand, but maybe what's in the book is not correct, because Mother Nature works in a simple way. That I'm convinced. And if the mechanism that we're talking about, that we're seeing, that we're reading, is complicated, I scratch my head and wonder: is it possible that I can't understand it because of my own limitation, or is it possible that something got into the textbook that is not correct, put forth by some, let's say, some famous person, accepted by many people, now in the book for generations, and we presume that it's true. But it might not be true. It might be that the often complex mechanisms are simply erroneous. And there are some really fundamental concepts in the book on which we build, or on which physiology builds, or cell biology builds. And if those are not correct, then everything we build on that shaky foundation is also incorrect. So there you go. I mean, this is my motivation. I'm convinced that many of the concepts that we read are simply erroneous. They just don't work. I spent 2 decades, 2.5, maybe even 3 decades studying muscle contraction. And you can read the mechanism in the textbook. We've produced many results and many findings that are simply completely at odds with the mechanism that's in the textbook. It simply doesn't work. It was unfortunately put forth by a great and distinguished Nobel laureate, Sir Andrew Huxley, a towering figure, you know, the kind of figure where he would walk into a room and there was a sudden hush. It's God walking, and it's the great Huxley. And many of the people in the field would tend to genuflect in front of the great Huxley. But, you know, I think the man was sitting in an ivory tower. He was so important that people were reluctant to challenge him, even though the theory that he put forth simply is bankrupt. It just doesn't fit the evidence. If it doesn't fit the evidence, then, you know, you have to ask the question, is it right? Is it not right? And for so many reasons, for so many experiments that we and others produce, is simply blatantly out of accord with the prediction of the theory. It's a question, you know, that the emperor really does have no clothes. you got to face the facts. It kind of fits in with what's going on politically today, where disinformation has become very popular. It's so difficult to understand. So I think there's so much disinformation that exists in the textbooks, and particularly in physiology. And the consequence of that is, medical students learn from that, and they learn principles that are erroneous. So someone has to take the bull by the horns and change it. And this is my goal. It's not an easy goal because there's so much involved with physiology, but so many concepts that simply don't make sense. So I would like to attempt to revise that in a way of putting forth ideas, concepts that I think make more sense. I can't be certain that they're right, but they fit the evidence better than what we read today. So that's the essence. I could go through a few more details if you like.
Yes, I'd really love to ask you if you want to talk about the cell and cell physiology and
Sure.
where we've taken a wrong turn and what you would love to write correctively in your book.
Okay, well, okay, so one of the central issues in cell physiology that we have come as a community to believe is that so much is in the cell membrane. So many activities of the cell reside in the cell membrane. Take, for example, the simple one of sticking an electrode into a cell. You stick the electrode in, one electrode outside, and you measure a negative electrical potential, 50 millivolts, 100 millivolts, something like that. And we know this thanks to the amazing contributions of the same Gilbert Ling, who taught us about structured water. He invented the glass microelectrode, and should have gotten a Nobel Prize for that. But he and others were able to stick the electrode in and determine the negative electrical potential. So question is, it's so fundamental, how does it arise? And the way it arises, according to the textbook, is that the membrane has this gadgetry. It has pumps that pump ions in and out, and it has channels through which substances can flow. And the combination of these, without going into great detail, somehow gives rise to the negative electrical potential of the cell. Now, the inside of the cell is like a gel. If you examine a gel instead of a cell, they're rather similar, except that the gel has no membrane. Yet, if you stick an electrode, I need my animation here. You stick the electrode inside the gel, you get the same electrical potential as if you stick the electrode in the cell. So, it doesn't take a genius to think that, well, wait a second, if this has something to do with the gadgetry in the membrane, the gel has no membrane. How come you get the same result? So you got to start scratching your head and say, well, this concept might not be correct. And there are reasons of evidence and logic to lead you to the concept that this is pure nonsense about right now, the number of channels and the number of pumps that have been identified in the membrane, in each case, exceeds 1,000. And as Gilbert Ling pointed out, there ain't enough room in the membrane to accommodate all of these. But there are more reasons why it doesn't really make sense. A simpler interpretation of the negative electrical potential in the cell, and by the way, the gel, the same thing, is that it contains EZ water or fourth phase water, or structured water, as you like. And we found experimentally that this water is typically negatively charged. And so if the cell is full of this water, and the water has a negative charge, it's a no-brainer that you need to consider the possibility that this negative charge of the cell and the gel is because the water itself contains negative charge. It's not complicated. It's actually, very simple, which accords, I think, with the concept that I mentioned earlier, that Mother Nature works in a simple way. So this is one example of something really fundamental that goes on in cell biology.
Not to mention that it aligns with the new thinking that water is biologically dynamic. It isn't just a background medium for other things, chemical reactions to be taking place. So
totally,
yeah,
totally,
really
absolutely, yeah. The water plays a role in practically every important activity of the cell. And I discussed this in my earlier book, 2001, Cells, Gels, and the Engines of Life, presenting the evidence that the water is intimately involved with every important process. It's not just a bathtub in which the important molecules of life are bathed, by no means. And it makes sense if you're an outsider and you look in and you think that, well, the cell is 2/3 water by volume. And if you were to line up all the molecules inside the cell and count them, because the water molecule is so small, if you start counting, you find that more than 99 out of 100 molecules inside the cell are water molecules. You need so many water molecules to fill that 2/3 volume. And to think that 99 out of 100 molecules don't do anything, essentially, which is the standard view, it doesn't make any sense. Why are they there? And this is so fundamental a question about how cells work that it's necessary it's almost arrogant to think that 99 out of 100 molecules, they're really, they don't do anything. They're just sort of sitting in the background, like you immerse yourself into the bathtub with water. They're intimately involved. And so that's another issue. In fact, if you think about the so-called action potential, which is, I think many people know about it, it's a phasic change in electrical potential. So that occurs is a sort of trigger for the cell to undergo whatever its job is to do. And again, the genesis of this action potential is very complicated, according to the textbook. However, a simpler interpretation is that this change of electrical potential from negative to near zero, and then back again to negative. A simple interpretation is that the water is undergoing a change from fourth phase easy water, which is negative, to ordinary water, which is neutral, and then back again. And in my book on fourth phase, that'll be more in the physiology book, I want to deal with this because it's so simple to understand that the cell comes into action, like a muscle cell, for example, starts contracting. And just before that, there's an action potential, this change of electrical potential. A really simple way, again, based on evidence, is that the water is undergoing the change. It's a so-called phase transition involving the water and the proteins. They both undergo a massive change, and that's what allows, for example, the muscle to contract. But it's not just, yeah.
What I'm curious about is how this book would extend how do you wish this book to accomplish beyond what Cells, Gels, and the Engine of Life? What more are you hoping this third book is going to address?
We've learned a lot more since then. At that point, when I wrote that book, we didn't know about fourth phase water, easy water. We knew about water structure. And a lot of that came from Gilbert Ling, amazing pioneer. But now we've learned much more about the nature of that water, how it forms, and its characteristics. For example, we didn't know at the time I wrote that the water, the so-called structured water, now we say easy, fourth phase, was negatively charged, typically negatively charged.
Hard to believe. It's
Yeah,
hard
it
to
makes it-
believe that you didn't know that when you wrote that book.
Well, you know, it takes a while for.
Yeah, I guess so.
Yeah, we did the proper experiments, and you know, they're very simple and direct experimental results. So, you know, you have to take seriously what you find in the laboratory, and so all of this has evolved, and also my own thinking about mechanisms. The book was written more than 20 years ago. You know, 20 years, you hopefully gain some wisdom. I'm not always sure about that, but anyway, I have a passion to bring these ideas together. And as I said, I wouldn't be doing it if I didn't think the ideas had merit. But my detractors might think otherwise. But it really is time, because essentially physiology, basic human physiology, has hardly changed since the time I studied it when I was a graduate student several centuries ago, I think. So yeah, that will be an advance over cells, gels, and the engines of life. I think.
Everine, do you have any questions about this third, this beautiful plan for his future book? Do you want him to answer anything in it?
I was wondering if you are going into like more the field idea in that book, or is it more the electrical water focus?
By field, you mean electric field?
Yeah, the quantum
of the
field
Earth?
and the frequencies and.
No, I mean, at present, I hadn't planned that. You know, physiology book. If you look at, maybe you've read a physiology book, they're too heavy to lift. You know, and there's so much that you can put into it, and so I will restrict what's in the book to things that I feel I can make some contribution. And going into what you're suggesting will involve much more and go beyond what I think I'm capable of writing. When I was a student, I remember there was a guy named Arthur Guyton, Guyton, who wrote a physiology book and did it himself. Most physiology books are not written by one person because it's a horrendous task. And I'm really glad that my naturopathic doctor told me that she's going to keep me going for at least another 40 years of good health. So I have enough time, if she keeps her promise, if I have enough time to keep going and working on this. But there's just so much you can do, you know, and my life is complicated. So, but this is my passion. I really want to go there. And it has to wait, though, until the first two books are completed and out. And that's coming.
Thank you.
Well, let's get a little bit recorded on the structure of the atom, and then
Okay.
we'll spend more time on your book that you're closest to right now. But we're really trying to wade you out into the future as far as we can get you, and then draw back to
Thank you,
what
Gina.
you're working on.
You're so kind and thoughtful. It all started, like everybody, I was satisfied reading about the structure of the atom. It's been in the textbooks now for 5 generations. You know, if it's 5 generations, you think, well, my goodness, it's got to be right. It started with Niels Bohr around the turn of the 19th to 20th century, more than 100 years ago. And I think everybody knows there's a nucleus, and around the nucleus there are electrons that occupy certain orbits, and many of those, many of the details that we we read about have been supplanted in a way with the advent of quantum mechanics, which is you might say an amplification of the original model of the atom. And quantum mechanics is mathematics. It's abstract mathematics, and you can scratch your head and ask. And we all, or almost all of us, believe in that. But there's a question that's raised. You can scratch your head and say, does Mother Nature really work on abstract mathematics? A lot of people would say nature works simply, and if you need to depend on abstract mathematics to get the answer, you might raise some questions. But my first question that was raised is on the simple model of the atom was when I visited San Francisco to a cousin of mine who was actually in the water field, but more commercially. And we were having a chat over dinner. And he said to me, how come the nucleus doesn't explode? I said, what are you talking about? So he said to me, you got all those protons in the nucleus, and they're stuck there, and they're really close together. And what I learned is that if you got all those positive charges, that positive charges repel each other. And in the nucleus, those positive charges are so compact, so near one another. So why doesn't the whole thing blow up? And,
good question.
Yeah, good question. So, and the physicists answered that because they also thought it was a good question long ago, and they said, well, the reason it doesn't blow up is because inside the nucleus is a special force that holds everything together. It's called the strong force. This struck me. My cousin didn't know about this, and I just happened to be giving a talk in the physics department at San Francisco State. And I asked the same question after dinner. We're walking back from the restaurant to my hotel or my cousin's house. I don't remember. And I asked them the question, and they said, oh, the answer is very simple. It's the strong force. It's like the magic force. And so it struck me and my cousin as a kind of Band-Aid to cover a gaping wound. You put forth a hypothesis, and there's something about that hypothesis that is fundamentally weird, wrong. And you invent something. I know of no independent evidence for the existence of a strong force. You invent something to hold it all together to make sure it doesn't blow up. That's point one. Okay. It's possible, but you look for independent evidence, and it's not simple. Next question. We understand that plus and minus attract one another, just the same way that plus and plus repel one another. And a question arises, you got this nucleus, okay, with a strong force that kind of keeps it together. It's got just the right characteristics to keep it all together without doing anything beyond the nucleus. But you've got an electron, or now an electron cloud sitting here, and some more here, and some more here. And it's negatively charged. So the question is, well, if this is positively charged and this is negatively charged, two should come together and the whole atom should collapse. Right.
Not explode, collapse.
Collapse. So you got one explosion and you got another collapse. And then you start scratching your head. And the answer, according to the current theory, is, well, at least Niels Bohr, who was talking about the hydrogen atom, a positive nucleus, an electron out there. What keeps this negative charge away? He said the answer is it just does. It was his famous answer. And, in quantum mechanics, the answer is that you don't consider charges at the atomic level. Ordinary charge forces don't exist. And so, okay, well, gee, Why they don't exist? Well, when do they start existing? When you put two atoms together, or 100 atoms together, or what? Where do you draw the line between when charges don't matter and charges do matter? Because we know they do matter on a larger scale. So you need to accept this kind of reasoning. And then, another one is how come, according to quantum mechanics, there are different orbitals. So you've got the nucleus, you have one orbital here, another one. How does an electron know that it's supposed to be in this one or this one, but not in between? And you'd expect that this is really weird because electrons should repel each other. And if an electron comes in, let's say, how does it know whether an orbital is filled or not filled? How does it know whether it should reside in between the orbitals or in an orbital? Those are all questions. And yet another question is, how do you put two atoms together to make a compound? And the usual answer is, because you've got a nucleus here and you have a series of electrons, and you've got the same thing here, a nucleus and a series of electrons. And so when two atoms want to come together to form a solid, what happens is you've got electrons and you've got electrons, and you'd think they would repel each other. So the two atoms could never come together to form a solid. And the response to that is electron sharing. And I could never understand how the problem is solved by electron sharing. For me, it's difficult to fathom how you can form a compound with that. So you begin to add up these concepts or these problems, and the whole thing sort of doesn't make sense. It looks like a bunch of excuses are put forth for something that just doesn't work. And I sort of like to think about the naive student who's asked to come forth with a model of the atom. How does it work? And the naive student, let's say, has no experience, doesn't know about the Bohr model, which has been supplanted by the quantum mechanical model. And the student comes forth with something like the original Bohr model. And maybe the student is coming to my laboratory or someone else's laboratory. And my guess is the student would completely fail because there are so many obvious things that don't fit. Okay, now you might be surprised that when Bohr came out with the original model, the chemists had a really negative opinion. And the famous chemists of the day, 100 years ago, said, I don't remember the quote exactly, but this doesn't explain even the simplest chemical reaction. It was meant to, but it doesn't. And the important chemists of the day were absolutely negative. But this was the era of physics. The physicists dominated the beginning of the 20th century, and a string of Nobel Prizes and such, but not the chemists. And so the physicists won out, and the physicist model held the day, and that model stands. But most people don't realize that the chemists absolutely rejected that model because it simply couldn't explain the simplest chemical reaction. And I agree with the chemists. There are real problems. And the chemists went on to suggest so-called Platonic models, some of the most important chemists of the day. What does that mean? Platonic model means Platonic, it has the shape of a Platonic solid. And Platonic solids are ones that actually fit together without leaving spaces. When you go back to the essentials of the Bohr model, that doesn't, it doesn't fill space, because even if somehow these two atoms or more could come together, there's always space that's left over in between, because you've got two spheres that are coming together. So they thought, some of the most prominent chemists, they thought that the model the model should be space filling, and cubes satisfy that. There are some other shapes that fall into the category of plutonic solids. And so I think those guys were right on. It made sense. And also, you can think of stability. The atom has to be stable. You can't have something that suffers imminent collapse, as we were talking about, or explosions we were talking about. Once it's there, it needs to be stable. And I thought about colloid crystals. And colloid crystals consist of typically water and some solids, little particulate solids. And they somehow come together in a way that is stable, because you can have a colloid crystal and it will maintain itself in a stable way. It won't blow up or collapse. And so I've developed a model that's based on that concept, where you have a stable solids that can come together, form a compound. And it's very easy, because the compound can form if you have one charge here, another charge here, or even charges localized that complement one another. They stick. And it's very simple. You can get a compound out of individual atoms that way. So without diagrams, I think it's probably not useful to go on and on about that. But this is in general what I've been thinking, and it appears in the book that is under development right now. So sorry for the long answer to the short question.
We're following you with great curiosity. Everine, do you have any comments, questions? I see there's a couple in the chat. Do you want to ask your brother's question?
Bastian, do you want to? I think Pamela asked something.
Mm-hmm.
Well, she mentioned something about Jack Kruse, who is a neurosurgeon and who has studied quantum physics and applied that to medicine. And then Bastian said, then he may have the answer to synchronicity question, and how different frequencies in light and sound are eventually registered, experienced as happening at the same time. I don't know if this is really a question or if that were remarks. Mm-hmm. But maybe Jerry has something to say about this.
Well, I don't have much to say, except that energy from the environment is critical for this, because you need energy to create this so-called crystal, or crystalline atom. The colloid crystal is the same. It's basically infrared energy. The infrared energy, or heat, some of us would call it. We have a constant input from the sun and also from all around us. And this energy is necessary for constructing the colloid crystal. And if the atom is like a colloid crystal, then the energy from outside, perhaps this is sort of what Jack Kruse is talking about, is absolutely essential for the whole process. So I don't discount that one bit. I think outside energy is certainly involved in all of this.
Yeah. Well, that leads us to the latest book, the first book you're about to bring out. And I know we've had some private conversations around it, but I know you're challenging convention once again. And we'd love to hear you say, why did you want to write this book? It's not really a book on water.
No, it's not a book on water, but water plays a role. It plays a role, I think, in a central phenomenon that many of us don't know about, but the evidence is very clear, and it has to do with electrical charge, and especially charge of the Earth. All of it started for me with a Russian scientist, a very creative guy who was working in my lab for 6 months, Andrei Klimov. And Andrei was just about, after 6 months of experiments, was about to take off that evening to go home to Russia. And we had a conversation. I'm busy all the time, and I haven't listened to Andrei as much as I would like to. And finally, we had an hour-long conversation. And Andre was telling me about the electric field of the Earth. The electric field of the Earth? Andre, you must be talking about the magnetic field of the Earth, right? He said, no, electric field. Don't you know that the ionosphere is positively charged and the Earth is negatively charged? And in between those two, like a capacitor, you have an electric field that runs from there to there, and the Earth is negatively charged. I said, Andre, you must be on some kind of drug. You must be hallucinating. I began my career in electrical engineering, and no professor ever told me or even hinted that the Earth was negatively charged. We all knew that if you have a plug and you plug it into a receptacle, that third round prong is connecting to zero electrical potential. I mean, there was not even a hint that that might not be true. He said, well, I'm sorry, there must be something wrong with the American educational system. In Russia, every middle school student knows that the Earth is negatively charged. So, I went home scratching my head. I said, how can this be? And if it's true, it must be absolutely important, centrally important. And the next day in the morning, student working in my lab who was actually participating here was Adam Wexler. I saw his image there.
Right.
Adam was in the lab, and he brought me the lectures of the great Nobel laureate Richard Feynman, often referred to as the Einstein of the second half of the last century. And volume 2, chapter 9 is just full of evidence for the negative electrical charge of the Earth. And I found myself convinced because the evidence was there. And it is possible that maybe there are some limitations to the educational system here. We tend to forget things that may be important. And for me, this is absolutely central importance that the Earth is negatively charged. And a lot of things follow from that. And if I were to say there's one central theme in the book, it's that the negative charge of the Earth, because many things follow from that. If you deal with simple electrostatics, it means that, for example, take a cloud. And I deal with weather in the book. I've got 3 chapters. We don't understand weather. Even the atmospheric scientists, one of them whispered to me, sort of in secret, after we were together on a podcast interview. He said, the 2 things that atmospheric scientists really don't know is how evaporation occurs and how clouds form. And if you don't know how water evaporates and you don't know how clouds form, you don't know anything about weather. And so I've got several chapters addressing weather, and so I'll just tell you one question or one issue that's there. Why do clouds float? You look up there and you see a cloud, and it's sitting up there. If you were to take a very long ladder and climb the ladder with some jugs of water in your backpack, and you climbed all the way up to the level of the cloud, and you took out a jug of water and you turn it, the water goes down, right? I mean, there's no question about that. And yet, you're at the same level of the cloud, and the cloud contains water. So how come the water doesn't go down in the same way? What keeps the water up there most of the time? And it doesn't take a rocket scientist to figure out that, well, if the Earth is negatively charged, and the evidence, by the way, is that the clouds are negatively charged as well. We know that some clouds, at least, are charged because you see lightning, but it turns out that the evidence has shown that all clouds contain negative charge. It's just that most of us don't follow the evidence. So you've got an Earth that's negatively charged, and you've got a cloud that's negatively charged, and the 2 repel each other. And so you can imagine that if the cloud has negative charge up there and the Earth the cloud will, if it has a lot of negative charge, the repulsive force will be huge and the cloud's going to be sitting high. If it has less negative charge, the cloud will be lower because the repulsive force is smaller. So you can even understand the enigmatic appearance of stacks of clouds. How do you explain that? You can sometimes, from my home in Seattle, I look out toward Mount Rainier, and I can often see atop Mount Rainier. Sometimes you can see 3 or 4 clouds stacked on one another. And at other places in the sky also, sometimes you see a dark one and a light one, and they're sitting at different heights. Easy to explain if you understand that clouds can contain different amounts of charge, and there's a natural explanation. That's why the clouds are floating. Similar question is, what turns on the rain? You can have, as we see very often in Seattle in the wintertime, we're just so hungry for sunlight, but the clouds tend to dominate. So you look out and you see some really ugly looking, gray, ominous looking clouds. I shouldn't say ugly because they're not really ugly, but they're ominous looking. And sometimes you get no rain, and other times you get rain. So who turns the switch? How do you explain that? No, nobody understands this, but I think the answer actually is pretty simple, and it's based on electrical charges, and it's based on a principle called Faraday Induction, and that is a simple principle. Every physicist knows it. If you've got, let's say, you have a positive charge, negative charge here, it will induce positive charge on the surface nearby, and the two will attract one another, and so you always get an attraction. And it works if these two are sufficiently close. If they're far enough away, then the effect is very small. So you can imagine about one of these, if you start with, say, one of these puffy white clouds, the kind with the cauliflower tops, the kind that you think could be the abodes of angels, just sort of tiptoeing on top, very pleasant, quiet. And then a front comes from a distance, and typically those fronts contain positive charge. Mm-hmm. So those positive charges come, and oh, hey, a negatively charged cloud. How interesting. So those charges then begin to attract and reduce the negative charge of the cloud. So the cloud has less negativity because it's been joined by positive charge. What happens? It descends because the repulsion from the Earth is not so strong anymore. And you get more of this positive charge, and it descends further. And once it descends sufficiently, it's still got negative charge. Once it descends sufficiently, this negative charge can induce positive charge locally, just right underneath it, you see. So then you have this attractive force. And this attractive force pulls the cloud down even further. Rain clouds deliver rain when they're low, not when they're high. And when the force gets sufficiently large, the droplets get pulled from the cloud. And that's why you can experience sometimes pounding rain, because they get pulled. It's not that the droplets actually drop, they get pulled. And the evidence from this is so interesting. 10 years ago, a group published a paper in Nature, and they did high-speed video of falling raindrops. And what they expected was very simple. If you have a droplet that's falling, like anything else that's falling, it experiences, it accelerates, and it experiences acceleration that reaches a terminal velocity. It won't go faster, it'll keep going at that speed. That's typically what happens. And you can easily calculate what that speed should be. They did high-speed video, and they tracked individual raindrops. And what they found is, at times, the raindrops fell at 10 times that terminal velocity. And their conclusion was that something is pulling the raindrops down. And they didn't know what it was, or maybe the editors of the journal wouldn't allow them to speculate on what it was. So, but they said, you know, that's the only conclusion that we can draw. And this is, I think, you know, a fact. Something is pulling the raindrops down. I said a moment ago that you can experience this pounding rain. And I think the answer is what I just mentioned. It's Faraday induction. Inductive forces are always attractive, and they pull the raindrops down from the cloud. So the answer to the switch, so to speak, is not complicated. It's very simple. You need a sufficiently large inductive force, electrostatic, to pull these raindrops down from the cloud. And I think that's the switch that takes a dark cloud, and if it reaches this threshold where the inductive force is large enough, you get rain. If it doesn't, you don't get rain. So the switch is actually very simple. And maybe I should stop there. I don't want to get
I just remember, Jerry, reading, you know, I looked at your first chapter on this book, we were talking about it, and you made a case that electric charge is as profound a force as gravity, that we don't yet understand. And I was very struck with that. And I can say we certainly look forward to hearing more, reading more about that. So get your son to get his work done so we can get that book out.
Believe me, I'm working on it.
I know you are. We're all behind you. We're all waiting for it. And I do think that electrical charge, the potential for it to be understood as important as gravity and gravitational forces, it's just a new question to think with that is going to lead us, you know, to some extraordinary new thoughts on what actually is running the show. Where are the mechanisms, or where do we find them? Everine, I'm going to pass to you. Are you watching the chat? Are there questions?
Yeah. I was seeing some interesting questions. One, for example, about the two different principles that Olivier here has been found when testing different water vitalizers. And he says there's two different ones. The one is creating the swirling of the water, and one is just changing the water by appearance or the touch of a substance. So does that have anything to do with your theory on electrical charge? Can you explain it, or is there something else happening to the water that he might be experiencing?
Are you asking Olivier or asking me?
No, Olivier is asking us. Yeah.
I'm not sure. Could you maybe?
He says, I have also tested different water vitalizers. You can sense a difference in the feeling of water. I see two different principles of devices. One is by creating some swirling the water, and the other just by the appearance or touch of a substance to the water. What is happening with the water?
Okay, well, it's a difficult question. I will, you know, propose an answer, but I'm not so sure that it relates directly to the material in the book. But you know, since the time of Schauberger, people have understood that vortices create living water, and I'm inclined to think it's probably true. However, you know, I've looked for experimental evidence, clear experimental evidence that that's happening. I haven't found it yet. We tried some experiments in our own laboratory to see what happens when you vortex water, and there was some indication that perhaps the vortex creates structure in the water. But the effect was not strong, and the experiments were not done very well extensively. So it would be great if somebody could actually do the experiment and make the test to see what's going on. I think it's likely, although the evidence is not in yet, likely that the vortex is creating structure, and that that structure also contains charge. So you may have, on the surface of the vortex, you may have a region of easy water that contains negative charge. And if that's the case, it might explain the shape of the vortex. It might explain the fact that vortex water is different from unvortex water. But as I said, the experiment, at least the evidence I've seen, has not yet been conclusive enough or extensive enough to test that hypothesis. It's not so easy because you have to make the measurement during the time that you have the vortex, because if you stop the vortex to make whatever measurement you want to make, it's possible that whatever structure might have been there, it's just dissipated quickly. So I guess that's as far as I could go on a question like that. Yeah. But thank you for the question.
Yeah. Maybe one question more closer to what you were talking about. Pamela is saying that she learned from Walter Jenne in Austria that bacteria rising up from the forest floor are an important factor in the formation of raindrops. Could that relate to your theory and what you're saying in your book?
If I understand the question correctly, there are bacteria in clouds. However, I mean, yeah, that's, and some people opine that in order to form a cloud, you need some nucleation entities like bacteria, for example. I'm not sure that's true, even though clouds do contain bacteria. So you can imagine that bacteria, other minuscule organisms and such, even salt, will rise up if they've got the right electrical charge. Bacteria have the charge. Raindrops or droplets typically have negative charge because they're surrounded by an easy shell, which confers their spherical shape. Otherwise, you'd have amorphous shapes. So yeah, I mean, you can find them in clouds, but the evidence we have is that the clouds can form without them. The essence is water, and the cloud consists of little droplets. Droplets on the order of 10, 20, 30 micrometers. And the droplets are held together in something just like colloid crystal. That is, you've got negatively charged droplets and you've got a positive charge in between. And it's a stable situation. You have many of these dispersed droplets. It's stable, so these spherical droplets don't necessarily come together or completely dissipate. They're held in a stable situation. And that's what you see when you look up at a cloud. You see a whole bunch of little droplets at given spacing between them, held together in a stable way. It doesn't mean that they're there permanently because, I mean, that stability, because you see clouds undergoing metamorphosis, changes. You can just stare up at the sky and see a cloud growing or dissipating. They're active,
but like a rabbit. It can look like a bunny. It can look like a lion.
It absolutely can. Yeah.
Well, Jerry, we only have a couple of minutes left, and I'd love to ask you the question, what is it you would like to see people applying science to? What research do you wish you could see become on board? What's the future that you'd like to see some people investigating beyond your own work? Who would you like to ask to go do something?
Good question. What I advocate is a search for fundamental truth, and in every field. And to get there, you need to dig deeply. You need to go beneath the surface and look at the foundational concept, because if the foundational concept is not valid, anything that you build on that will be utterly complicated and incorrect. And a lot of scientists are, because of the way the system works, are spending a lot of time dotting the I's and crossing the T's, instead of digging down and asking the fundamental question, about the emperor's clothing. What's true? And there's a kind of fear among a lot of scientists, fearful of doing that, because we all have to put food on the table, and We need money to do that. And there's a competition for research money. And people who venture to ask these so-called radical questions about foundational truths, they mostly suffer. They don't win. And there are so many examples of that. And so the canny scientists who are, everybody's interested in finding truth, but putting food on the table is equally important. And they know that they have to kind of stick to the mainstream views. And if they do that, they might succeed, particularly if their work is prodigious enough, quantitatively. And that's the way to succeed in science today. And this is not the way.
We're leading a new way, Jerry, and we're thankful that you're part of that story, and we're grateful for your work, and we love being a family around you, and we thank you for this time and peek into your future work. It was a great little tour, and any way that any of us can be of any service to getting your ideas forwarded, we are here for you. We have to give up the room, so we're going to pass it on. I think Pamela is taking over from here, but Jerry, we love you. We bless you. We thank you for your time that you gave us and your thoughts on where you're going, and we're all behind you.
Thank you, dear Gina, and dear Everine. A great pleasure to be associated with all of you.
Yeah.
Thank you.
Yes.
And we're glad to pass the room on to you, Pamela. Blessings on the next hour to all of you. Okay.
Yes.
Thanks, Jerry.
Thank you.
Thanks,
Sure.
everyone.
Pleasure.
Thanks, Sebastian. Bye-bye.
Bye.